Hi, so first I would like to thank the organizers for the great opportunity to speak in this international seminar. And today I will present you a joint work with Adi Dickstein, Leonid Polterovich, and Frol Zapolsky. And the topic of our talk will be, as the title says, big fiber theorems and ideal valued measures in symplectic topology. So I'll start by reviewing some big fiber theorems and explaining what I mean by a big fiber theorem. Then we will discuss ideal and valued measures, which are a tool introduced by Gromov, and he used it to prove some big fiber theorem. Then we will describe our adaptation of ideal valued measures into the world of symplectic geometry, which we call ideal valued quasi-measures. And armed with that tool, we will revisit big fiber theorems, this time from symplectic viewpoint. And we will conclude with some remarks on rigidity from this viewpoint and some notes on the construction of our IVMs. So what are big fiber theorems? So in various fields of mathematics, you see theorems that suit the following template, that for any map in a certain class of maps, you have a fiber which is considered big, where of course the notion of size of the fiber varies from field to field, from topic to topic. And I plan to review three such theorems. The first is called topological center point theorem, which has origins from Rado, but I will review version by Karasov. And this version has some kind of a combinatorial topological flavor. I will also present Gromov's torus fiber theorem, which is more topological in nature, and the Polterovich non-displaceable fiber theorem in symplectic topology, which is symplectic. And one of the main goals of this project was to take this idea of Gromov's ideal valued measures, which can be used to prove the first two theorems that you see here. And it's a good time to remark that the third theorem here, the non-displaceable fiber theorem, has been proved using totally different methods that come from spectral invariants and quasi-states. And the idea is to take those Gromov ideal valued measures and together with the Varolgunes relative symplectic homology, we are going to put all three theorems on equal footing. So let Y denote a metric space of covering dimension D. And by that, it means that any covering can be refined such that each set intersects no more than D plus 1 sets. So it's a topological notion of dimension. And let P be just any integer. Then the topological center point theorem says the following. So fix N to be the product of P and D plus 1, and take delta to be the N simplex. Then, for any continuous map from that simplex to Y, we have a fiber that intersects all the PD dimensional faces of the simplex. So here, the notion of size, a fiber is considered big if it intersects all the faces of high enough dimension. And for affine maps, it was proved by Rado, but it's actually true for any continuous map. And just an example of what kind of statement this theorem claims. So take the 2 simplex. So we set N to be 2 and D and P to 1. And we took just some projection on a line. And indeed, there is a point such that the fiber over it meets all three one-dimensional faces of the simplex. Now, Gromov's torus theorem starts with a very similar setting. So again, Y is a metric space of covering dimension D. And basically, this notation is going to follow us throughout the talk. And now fix N to be some number greater than this product of P and D plus 1. Then for every continuous map from the torus to Y, we have a fiber such that the rank of restriction in cohomology is big, namely at least 2 to the pth power. So here the notion of size is basically having a large rank of the restriction map in cohomology. So what kind of statement does it claim? So take a 2-dimensional torus and let us project on the first factor. So I'm projecting on the factor that goes this way. So over any point, the fiber is a circle like drawn here in red. And indeed, the image of the restriction map in cohomology, well, it contains the unit element of the cohomology ring, and it contains what I denoted by dy. Well, if they denote by y, the coordinate that just goes along the circle. So indeed, we have a two-dimensional image. So the rank is 2, and it is 2 to the power 1, which was p. So here you can see that the fiber is just a circle which has some cohomologically non-trivial circle. So that's the kind of type of fibers that Gromov guarantees us. Now, for the non-displaceable fiber, the setting looks a bit different. So let me recall it for those who don't know. So we start with a closed symplectic manifold, and we take a map to Rn such that every 2 components of that map Poisson commute. Then the theorem by Antov and Kolterovich says that there is a fiber such that it is non-displaceable. And just an example, the simplest example is if we set everything to 1. So we have a 2-dimensional symplectic manifold. Here I took a sphere, and I have a function to R, just in this picture, the height function. And indeed, one of these fibers has to be the equator, which we know to be non-displaceable. So let us now discuss the main tool that can be used to prove the first 2 theorems that we've seen. So it's called ideal valued measures. And let us fix A to be a graded skew commutative associative unital algebra. But in reality, just think of the Czech cohomology ring of some compact houses of topological space, because this is what we are trying to model. So in everything we discussed, let's keep in mind that A is a cohomology ring. And an ideal valued measure is an assignment such that to every open set, we are going to assign some graded ideal in that algebra, such that certain list of axioms hold. And what these axioms do, they model the behavior of kernels of restriction maps in cohomology. So think of mu of a set to be the kernel of the restriction to the complement. So we want to see which classes get eliminated when we restrict to the complement, and this gives us some kind of ideal valued measure of the size of the set from the perspective of topology. And the axioms are basically quite natural given this main example to keep in mind. So we normalize, so the measure of the empty set, it's the kernel of the restriction to its complement. Well, complement is everything, so we restrict nothing and the kernel is 0. And the measure of the whole space, it's the kernel of restriction to its complement that is restricting to the empty set. So it's everything. We have monotonicity. We have a continuity property. So if an open set U is an ascending union of sets, then its measure is the union of measures. And this is the reason I chose Czech homology as our main example, because Czech homology is continuous in that sense. We have additivity for these joint sets, which is some kind of shadow of the Meyer-Vietoris property. So in Meyer-Vietoris, if 2 sets are disjoint, their intersection is the empty set, and this axiom, in some sense, captured this. We have multiplicativity, so we want that the product of measures of 2 sets will lie in the measure of their intersection. And the way to think about what this models is if we take, for a second, a simplified de Rham model. So if we take some differential form supported on U and another differential form supported on U prime, their wedge product is supported on the intersection. And this is actually even truer in generality, and this is the type of behavior that this axiom models. And the last one, which called the intersection axiom, says that if we have 2 sets that cover X, then their measure of intersection is the intersection of measures. And again, this is some manifestation of the Meyer-Vietoris property. So it's basically an object that gives us some ideals associated to open sets, and it satisfies some axioms which are reminiscent of the axioms of measure. Therefore, it's called ideal valued measure. It was introduced by Gromov, and he actually used it to prove his torus theorem. Now let us review two main examples to keep in mind. So the first example is the check cohomology IVM, which I already presented. It's just the kernel of the restriction map in cohomology to the complement. And the second example to keep in mind is the push forward IVM. So given any set and an IVM on it, we can generate new IVMs on other sets just by pushing forward the IVM via continuous maps. So I get a new IVM on the set Y, and now this IVM has nothing to do with the cohomology of Y. By the way, I cannot see the chat, so if there are any questions, please let me know at any point, or just speak. And you know what? It's a good point to stop for questions now before I go on, if there are any. Okay, great. So I'm going to discuss a few pointers on a proof of a Karasov's theorem using this language of IVMs to demonstrate the axioms and how they interact. And the proof that I'm presenting is a variation of Karasov's original proof. So in his original proof, he didn't use the notion of IVMs, but he did something very close to it. So the whole theorem lies on a statement that is actually just an abstract statement on IVMs on topological spaces. So let Y be a compact metric space of covering the dimension.
Sorry, can I ask a question? It's a bit late. It's about the previous slide.
Sure, of course, yeah.
So you said you specifically emphasized that you want to check cohomology. So singular cohomology doesn't work in example 1.
So singular cohomology on the nose will fail, will not satisfy the continuity axiom. So
can you show us again what the continuity was?
Yeah. So we want that the measure of an ascending sequence of a set will be the union of measures.
Okay,
so it's basically saying that the measure of certain limit is the limit of measures for correct notion of limit. Now, this can be remedied. You can use the singular cohomology, but you have to change a little bit the definition. So you have to take some kind of regularization. You need to approximate the set with compacts or open sets and take the limit of that. So you kind of force it to be continuous. So I didn't want to go into it. But it's a good question because this notion will reappear later.
Okay, thanks.
Welcome. So we have a Y compact metric space of covering dimension D, and pick some algebra, and let I be an ideal such that its D+1 power is not 0. And mu just any IVM on Y associated to this algebra A. Then the claim is that the collection of all compact sets such that the ideal lies in their measure has a non-empty intersection. So in a way, having such an ideal gives you a notion of a very large set. So a set, you can think of it as being very large if it has this ideal in its measure. And what this theorem says is that such sets are so large that actually their entire collection must intersect. So pictorially, you can just see that for every set, we associate some ideal, which is drawn here as a plane. All these planes have to contain our I, this is ideal that has this special algebraic property. And the statement of this theorem is the existence of this green point, that the intersection is non-empty. And to prove this theorem, it follows only from properties of metric spaces and the axioms of IVMs. So basically assume the contrary. Then the collection of complements of all such Z's in this collection is an open cover. Now, there exists a lemma due to Palais that says that for a space of covering dimension D, we can refine any cover such that it can be colored by D+1 colors, such that the sets of the same color are disjoint. So we break the cover into D+1 collections. Each of them is a collection of disjoint sets. And now, just put K to be the intersection of the complements of all the sets in that cover, of the same color. Then by multiplicativity axiom, the product of measures of all those k's should lie in the measure of their intersection. And here we are intersecting complements to sets in a cover. And since it's a cover, every point has to not lie in one of the complements. Therefore, the intersection is the empty set, that is 0. So multiplicativity guarantees that the product of all those measures is 0. On the other hand, if we show that I belongs to each of those sets, these ki's, then we are done. Because then we will have that this product should contain I to the d plus 1 power, which is not 0. And this follows from the intersection and monotonicity axiom. So intersection axiom tells us something about measures of intersections of a set of collections such that they pairwise form a cover, and monotonicity tells us something about enlarging sets, which is dual to refinement. So I'm not going to get into all the details, but just wanted to give you the basic skeleton of the proof of that theorem. Now, this talks about some point in the intersection. Karasev's theorem talked about some fiber intersecting some sets. So the idea here that if we have any compact Hausdorff space X and IVM on it, and Y d-dimensional as before, and I an ideal as before, then any continuous map from X to Y has a fiber intersecting every compact set with this property that its measure contains I. And this basically follows from applying the previous theorem to the push forward measure. So we push forward the measure from X to Y, we apply the theorem there, and then it's just verification, the set theoretic level, to see that it indeed has such a fiber. Now, to get from this corollary, the Karasev's topological center point theorem, we have to do the following. So let me just remind you the formulation. So formulation was that for any continuous map from the n-dimensional simplex, we have a fiber intersecting all the pd-dimensional faces. So to apply the previous theorem, all we need is an algebra A and an IVM mu on the simplex, such that there is some ideal whose d plus 1 power is not 0, and every pd-dimensional face has this ideal in its measure. And the way to obtain such a measure is to consider the moment map from CPN to the simplex. And this moment map, if you recall, has this property that the pre-image of a face of the simplex is a complex projective hypersurface of the same complex dimension. So all one has to do is pick as mu the push forward measure from CPN, where I take the cohomological IVM on CPN and I push it forward to the simplex. And as my ideal, just pick the Poincaré dual to the PD-dimensional complex hypersurface. And from here, just routine verification to see that intersection is indeed non-zero due to the fact that in intersection, codimension increases. And of course, every PD-dimensional will have the ideal in its measure because the ideal is the Poincaré dual to this hypersurface, and the measure is about restricting to the complement, so I kill the Poincaré dual. So we get a Karasev's theorem. And actually, Gromov's theorem has a very similar structure, which I will not go into due to time constraints, but the idea is that it has two ingredients. The first is to prove some abstract center point theorem, that there exists some point such that the codimension of the measure of it, of the restriction of the measure of its complement is at least some bound, and then use the push forward IVMs to translate some abstract center point theorem to an assertment on fibers. So you can see that here, the measure of the complement of a point has to do with the rank of a restriction, because the measure of the complement will have to do with restriction to the complement of the complement, that is restriction to Y in cohomology. And codimension has to do with ranks. So this is all I want to say on Gromov's storage theorem. And we will get back to it once we examine the symplectic version analog of this theorem. So I want to introduce now ideal valued quasi-measures, which are our symplectic analog of that story. And the goals are threefold. So we want to adapt IVMs to the symplectic settings. And we want to be able to apply those center point theorems that we mentioned earlier. And we want to explore the symplectic rigidity via this, through this ideal valued point of view. So for that, we need to introduce some definitions. So given a closed symplectic manifold M, a map from M to Rk is going to be called involutive if all the components of this map Poisson commute. So this is like an integrable system or something like that. And more generally, any smooth map from M to some topological space B will be called involutive, sorry, to some manifold B will be called involutive if for every pair of functions smooth on B, their pullbacks Poisson commute. So this is a generalization of the first definition to targets which are not Rn, but some manifolds. But actually, it's a special case of the first definition because we can always embed B into Rn and use the first definition. So basically, you can keep in mind whichever definition that you want, but the idea is that an involutive map is a map such that its components Poisson commute. Now we say that two compact sets commute if there exist two Poisson commuting functions, f and g, such that k is the zero set of f and k prime the zero set of g. And we say that two open sets commute if their complements commute. So commuting sets is some kind of way to translate this notion of Poisson commutation from the world of functions to the world of sets. And let me present two examples. So first example is if we have two domains with non-intersecting boundaries, they form commuting sets. So in this picture, I have two caps, each of them having area more than half of the disk. So they intersect, but they do not intersect along their boundaries. So I have the blue cap going all the way down here, and I have a red cap going all the way down here. And the reason that they commute is that one function will be constant when the other varies. So the Poisson bracket will be zero. On the other hand, in dimension 2, if the boundaries intersect, the sets do not commute. Because I will have two symplectic gradients with pointing at the directions which are non-linearly dependent. And now we can introduce our ideal valued quasi-measures. And basically, the definition is exactly the same as an IVM, only that we replace the multiplicativity axiom by a weaker axiom, which we call quasi-multiplicativity. We demand that the product of measures of two sets lies in the measure of their intersections only if those sets commute. So it's a kind of a symplectic adaptation to the previous notion. And actually, to adapt the symplectic setting, we are going to require two extra axioms. So the first is an invariance. We require our IVQMs to be invariant under a symplectic isotopism. And we want a vanishing axiom. That is, if a compact is Hamiltonianly displaceable, then there must be some open set containing it, which has the zero measure. Moreover, we want its complement to have full measure, which is basically encoding the fact that we want to see displaceable sets as small, that is getting zero measures and their complements getting everything. And one reason why we add those two extra axioms is that basically we can construct such an IVQM which satisfies those two axioms. So why not use them? So our main theorem is that on any closed symplectic manifold, we have an AIVQM for some algebra A. Now, secretly, this algebra is going to be the quantum cohomology, but this is not important now. And the upshot is that preimages of sets under involutive maps commute. Hence, using the push-forward construction, we can push IVQMs to regular IVMs under involutive maps. And since those big fiber theorems were presented by Karosev and by Gromov, they use the push-forward property together with some abstract theorem about IVMs. This allows us to gain symplectic analogues to Karasov's theorem and to Gromov's theorems. And just as an example for IVQMs, let's construct by hand an example on a two-dimensional manifold. So I'm taking the sphere, the S2, and it's enough to define our IVQM on a two-dimensional closed connected submanifold with boundary, because every other set could be approximated by unions, disjoint unions of subsets. And our definition is as follows. So tau of Q is going to be 0 if Q is contained in some smooth closed disk of area less than half, that is displaceable, and the full measure otherwise. So for example, this small cap here gets the 0 measure, but some neighborhood of the equator gets the full measure because it's non-displaceable. And that is indeed an IVQM. This can be either verified by hand, or for A being the quantum cohomology algebra, this will actually follow from our more general construction. I saw some unmuting in Montreal. Was there any question there?
No question. For now.
Great. So how does one construct those IVQMs? So our construction is based on a notion of cohomology due to Varolgunes. And he constructed something called relative symplectic cohomology, which assigned some homology K to every compact set of M. And it's called relative because this construction actually depends on the embedding of K into M. It depends on the ambient manifold. It is also a ring, which was proved by him together with Tonkonov. It comes with restriction maps. And it comes with Meyer-Vietoris sequence for pairs of commuting sets. So this is where commutativity comes into play in our story. Moreover, it vanishes for displaceable sets. And our construction basically is just take the usual construction of an IVM and replace the homology by this symplectic cohomology. Sorry, replace the check homology by this symplectic cohomology. So for every compact K, we just want to take the kernel of the restriction to its complement. Sorry, it should be for every open K, for every open U, sorry. But so basically we can discuss IVMs either on compacts or on open sets. And to achieve continuity, actually, one has to alter this definition a bit. This relates to Sobhan's question, because this symplectic homology is not known to be continuous. Maybe it's even not continuous. So we have to do some regularization procedure to force our IVM to be continuous. I don't want to go into this. And basically all the properties, all the axioms followed the same way as they would have followed for cohomology, usual cohomology, except for the quasi-multiplicativity, where this is the non-trivial part, and here it required some new ideas. And what I want to do now is revisit big fiber theorems, now armed with this symplectic tool. So we can get a quantitative version of the Entov-Molterovich non-displaceable fiber, which says that every involutive map from M to any space B has a fiber where the codimension of the measure of its complement is at least 1. And note that displaceability implies that this codimension is 0, because had the fiber been displaceable, then by the axioms of IVMs and IVQMs, it's had this fiber been displaceable, then by the vanishing axiom for IVQMs, the measure of its complement should have been everything, so the codimension should be 0. So in particular, this theorem says that this fiber is non-displaceable. But moreover, Gromov actually provides some lower bounds for this codimension using the algebraic structure of the algebra underlying this whole IVQM business. And so actually we might get a better bounds in some cases. So this is the analog of Gromov's theorem in this story. It's actually some generalization, extension of the Anton-Foterovich non-displaceable type. As for the Karasov's theorem, the symplectic, the topological center point, we now get some kind of a symplectic center point theorem. So if we can find some ideal I such that its d plus 1 power is not 0, and we take some B to be a manifold of covering dimension D, then we get that every involutive map from M to B has a fiber that intersects all the members in this collection, the collection of sets, such that their measure contains I. So in Karasov's case, this collection corresponded to the PD dimensional faces of the simplex. Here, we will see examples where it corresponds to totally different sets, but this is the symplectic analog. So it's basically a source of new kind of examples of symplectic rigidity, where you can think of this notion of fiber is large if it intersects some kind of large collection. So it's a new type of rigidity. And let us just show an example of applying this theorem. So take the 6-dimensional torus, the symplectic 6-dimensional torus, with the pi, qi coordinates on each component. And for every triplet of points, ABC, on a 2-dimensional torus, let us consider 3 coisotropic subtori that are just obtained by restricting certain coordinates to either A, B, or C. And basically these tori were chosen such that, so first of all, we can compute SH for a sub-coisotropic tori in symplectic torus. And it actually, their IVQM coincides with their usual IVM for a usual cohomology in this case. And those tori were basically chosen such that if we take their union, it kills, its measure kills enough generators in cohomology to contain an ideal with the desired property that T to the ideal to some power will not be 0. And now our theorem says that every involutive map from T6, product of T6 with a sphere, to a 2-dimensional space has a fiber that intersects all sets of the form product of such union of tori with an equator. So the reason we added this sphere to this example is because we want to get something that is genuinely a symplectic phenomena. Because if I would have just removed the sphere here and I would have taken maps from T6, then this fiber intersection property would have just followed from topology, because as I said, the IVM computation coincides with the IVQM. But on a sphere, we have the equator, for example, which has a very different IVQM measure versus an IVM measure. So this is the theorem. And the involutivity is essential for this property to hold, because otherwise, if I drop the involutivity assumption, I can just take a map from the 6-dimensional torus times sphere to the sphere, symplectic projection, which is highly non-involutive. And then for every point on this sphere, and for every point on this sphere, I can find an equator not passing through it. therefore, the fibers of that point will be disjoint from any set, which is a product of that equator times anything. So it's very much doesn't hold without non-relativity. So in the remaining time, I want to discuss some facets of rigidity and discuss briefly the construction in more detail. So before we go on, any questions on what we just saw?
So what's stopping you from generating? So do you have more examples like this torus stabilized?
At the point, no. So
and the problem is like computing this.
The problem is computing this symplectic cohomology. So in a spherical manifold for certain types of subsets, it is easy to compute because it coincides with the topological case. So basically, I might be able to generate more examples which are the form of some topological rigidity times a sphere. But to do something more than that, we need to compute something new in SH.
Mm-hmm. Thanks.
Welcome. So now let's denote the symplectic homology IVQM, which we discussed. And we say that a compact set in a symplectic manifold will be called SH heavy if its measure is non-zero. So for example, if we take some circle on a torus, it's SH heavy because, as I said, its IVQM actually coincides with the cohomological one. On, for example, the equator on a sphere is SH heavy because its measure is the full measure, and you can see this by the fact that its complement can be approximated by a disjoint union of a displaceable disk, which has zero IVQM. And so they satisfy some properties. So first of all, they are non-displaceable by symplectic isotopes due to the axiom. And moreover, if I have two sets such that the product of their measure is non-zero, so first of all, trivially, both of them must be SH heavy because these two cannot be zero. But moreover, we can show that one is non-displaceable from the other. So as an example, just again, let's think topologically for a second. Those two circles, they are already displaced from each other. And indeed, their product of IVQM is zero, because if I compute their measures, each of them will contain the volume class in cohomology and the class which I denoted dy, which was corresponding to y going in this direction. And dy wedge y is zero, and everything, if I'm multiplying with the volume class, I just get to a too high rank, and it also vanishes. On the other hand, you can see that in this example, with these two circles, their product of measure is non-zero because I will have in the product dy wedge dx, which gives me the volume form, which is non-zero. So this is, of course, a topological example, but as I said, we can upgrade them to a genuinely symplectic example using stabilizations. So consider the product of this green torus, the green circle and the green circle here. So I have a product of two tori sitting in the product of T2 with S2. So one is the green torus and the other is the cherry colored torus. And we can get from our result that they are non-displaceable from each other. Now, this has been proved previously using Lagrangian spectral invariants, Lagrangian quasi-states by Kawasaki, I believe. But perhaps if we gather new computations of SH, we can probably use this method to get something genuine in it. Of course, as you can see, they are smoothly displaceable because I can just displace the circles in the sphere. So So it's genuinely a symplectic phenomenon. Now, for the proof of this intersection property, well, it's basically follows just by following the axioms. So assume I have some isotopy that displaces K from K prime, then I get that the image of K is disjoint from K prime. Hence, these two sets commute. Disjoint sets commute trivially, because one function is constant when the other is varying. Then by quasi-multiplicativity, I'll have that the product of measures here is going to lie in the measure of the intersection, which is empty set, because it has been displayed. On the other hand, invariance claims that the measure of the image has to have the same measure of the original set. Hence, we cannot have that their product is non-zero, and that's a contradiction. So it's once you have the machinery in the back of your mind, this thing is just routine verification from the axioms. Yeah.
Is there implication between this SH heaviness and just the standard heaviness?
You anticipated the next slide.
Oh.
So there exists an older notion of rigid sets in symplectic manifolds called the heavy sets due to Entov topology. And they were defined using the partial quasi-states, which are certain, say, functionals taking Hamiltonians on M and giving us back a number, which is generated by some kind of a homogenization procedure on spectral invariance relative to some idempotent. And one says that a set is heavy if for every such Hamiltonian, its quasi-state is at least the infimum of K. So K is heavy if somehow the values of F on K govern this result of the quasi-state. And they enjoy very similar properties. So they are non-displaceable. And they need not necessarily intersect. So two parallel meridians on the torus do not intersect, and a meridian and a parallel did intersect, as we see before. But it's very unclear how to detect intersections in this language, in contrast to the SH-heavy formulation. Now, of course, it's very tempting to conjecture that heaviness actually implies SH heaviness. And the reason it's tempting to conjecture it is because we have proven it for a simple case. We can show it for index-bounded incompressible domains in a spherical manifolds, which these conditions basically allow us to reduce the computation almost to the topological computation. So our conjecture is that indeed heavy implies SH heavy. And on the other direction, it's more speculative because heaviness says something about the asymptotic growth of these homogenized spectral invariants, of those spectral invariants, C, K, F. But at least from what we have examined on SH heaviness, at least on the node, SH heaviness just, it looks like it describes some kind of property along the lines of those sequences going to infinity without telling you something more delicate about the rate. So maybe there is something deeper here. Maybe there are some restrictions on possible rates or something like that, but the other direction is more speculative. So I wouldn't call it a conjecture, maybe a speculation.
I don't remember what index bounded means. Does it include convex embeddings of convex domains?
I think not necessarily. So index bounded means that in every index, you have a bound on the actions of the generators in that.
A bound from above, or?
Well, depending on your direction, like a bound away from zero.
Okay.
Can I ask you a question as well?
Yeah, sure.
Can I ask you a question as well? Sorry.
Yeah, of course. Yeah.
So there is a notion of super heaviness too.
Yeah, so super heaviness is when you replace this infimum with a supremum here. It's actually much stronger. And our conjecture or our, well, call it a soft conjecture because we haven't proven any result in the direction yet. But it seems that if you have full measure, that should correspond to super heaviness.
Uh-huh.
So like being SH super heavy should correspond to having full measure.
Super heavy should correspond to having SH full measure.
Yeah.
That's what you said. Now, super heavy sets, any two super heavy sets just always intersect, if I remember correctly, right?
Yeah,
now,
and this would follow from the multiplication criterion, because if we have full measure, then the product of full measures is not empty.
Now, I apologize if I already forgotten stuff from the just previous slide. So these examples of displaceability that you gave a couple of slides back, you mentioned here, these are not super heavy sets for some sort of, for the quasi-measure or whatever.
So are you saying whether those sets are super heavy? I think not, because they are product of a super heavy with a heavy.
Okay, no, they're not. Okay, great.
But indeed, on this factor, it has full measure. The part that doesn't see full measure is.
No, it's the torus factor.
Yeah.
Okay, thanks.
Welcome. So lastly, I would like to say a few words deep about the construction. So this is a bit more technical part. So let me just review what is a Varolgunes relative symplectic homology. So it's basically another step in the evolution of symplectic homology. So it all starts, symplectic homology starts with Floer, Hofer, then Vysotsky, Zilbach, Viterbo. You have contributions by Traynor, Bourgeois, Oancha, and many others. And the main idea behind it is to get some invariant of a symplectic manifolds or subsets using some limiting procedure on Floer cohomologies. And to formulate a Varolgunes version, I'm going to need the Novikov field and the Novikov ring. So these are just formal sums with some coefficients of some powers of t, such that the powers go to infinity. So they do not, the powers do not have any accumulation in finite value. And the Novikov ring is given by just restricting to a non-negative powers. So it's a ring. And given a Hamiltonian, let us denote by pH its set of one periodic orbits. And it could be graded by mod 2 Conlitz-Sender. And the Floer complex that we are taking here is generated by these one periodic orbits. So note, there are no cappings in this version. And the differential, it counts positive gradient flow of the action functional because it's cohomology. And basically to make up for the fact that it has no cappings, it's going to be weighted by the topological energy of the Floer solutions. So for the differential of some gamma minus is going to be a sum over all possible gamma pluses, then a sum over all different homotopy classes of cylinders going between those two orbits, and I count something in some moduli space of positive gradient flow, and the result is being weighted by the area plus some integral of the Hamiltonian on the destination minus the Hamiltonian on the origin. And the way you can think about it is, if I was in the aspherical case where I could have defined the action, then this expression just corresponds to the action difference of those orbits. And similarly, we have continuation maps, and they are also weighted by the topological energy. And again, if we had been in the spherical case, it would have corresponded to action difference. And since we are defined over the Novikov ring, we need the exponent to be positive. So the continuation maps are defined only once we go from some low Hamiltonian to a higher Hamiltonian. So only from the low Hamiltonian to the higher one. Now, how to cook from this a cohomology? So given a compact set, take a sequence of Hamiltonians adapted to it in the following sense that I want them all to be negative on K and converging to 0 on K and converging to infinity outside of K. Then the symplectic cohomological complex is going to be defined using the limit of those complexes associated to each Hamiltonian. And then this limit goes a procedure of completion. So we have a completion with respect to the t-adic topology. And so there are two ways to think about this completion. You can either just define it as an inverse limit of truncations where I kill each time powers greater than r, or you can just think of a metric completion where high powers of t indicate something being very small. And this completion also has a feature of making everything Hausdorff, if you think metrically. So if two things have a difference which is smaller than everything, then they become equal after completion. And its role is to eliminate the contributions of the upper orbits. So we have generators of the complex that come from orbits lying up here. And let us think, so it's some kind of algebraic procedure that essentially should eliminate the contributions of those upper orbits in the following way. So let us think on the simplest case. Say I had some critical point here, up here, and assume that it just was by the continuation map, it was just sent to some critical point above, then another above it, then another above it, etc. So as I said previously, the differential and the continuation maps are being weighted by t. So say that the action difference between each level is 1, just for the sake of thinking of it. So what you will have for this particular generator, you will have a map going between Novikov rings, each time multiplying by t until we get to the limit. One way to think about it, how to compute this limit, is instead of keeping Novikov rings and taking multiplication by t, just take isomorphisms to truncating from lower and lower places. So here I truncate from t minus 1, I truncate from t to the minus 2, etc. And then, in this point of view, multiplication by t is the same as just inclusion, because sending an element here and multiplying it by t is the same as saying that this element is included here, but now its image is some t multiple of something else. But in this picture, it's very clear to see that the limit is just the union, and the union is the Novikov field, which is a model which has no torsion. So if you plug it into this completion procedure, you'll see that at each step you are tensoring with torsion and you're getting 0, hence you get a limit of zeros. So basically, upper orbits contribute some summons which look like Novikov field in this limit, and completion basically kills those summons. And then the symplectic cohomology could be defined as a Novikov ring model as the homology of this symplectic cohomological complex. But what the version that we work with is after taking homology, we tensor with the symplectic, with the Novikov field, because we want to eliminate torsion. So basically, this torsion corresponds to some finite bars in cohomology, and we want to work only with the infinite rays. So this is Varolgunes cohomology, and it satisfies that for if I'm restricting my compact, I can construct using continuation maps, I can construct restriction maps. It satisfies Meyer-Vietoris for commuting pairs of subsets. And it was constructed by a product was constructed by Tonkonog and Varolgunes, making it a unital ring. And actually, the symplectic homology of the entire manifold is the quantum cohomology. Now note that while on the level of homology, everything behaves nicely, on chain level, everything is well defined only up to homotopy, because first of all, we are making those choices of sequences of Hamiltonians. And if we change those sequences, we will get not the same chain complex, but a different chain complex, which is homotopic to the original one. And second, those restriction maps satisfy it if I restrict from K to K prime and then to some other sets. So in cohomology, sorry, it's the same as restricting directly. On the chain level, this is not the case. So if I restrict twice or I restrict directly to some destination, I don't get the same chain map. I get the same chain map only up to homotopy. And this forces us to work in some kind of an infinity categorical notion where we have to take into account homotopies, homotopies within homotopies, etc. And now recall our IVQM. So it was just some kind of regularization of the procedure of just taking kernels of restriction maps. And as I said, quasi-multiplicativity is non-trivial. And the way we show quasi-multiplicativity is that we enhance this cohomology theory to contain also cohomology of pairs. So given a pair K prime inside K, I'm defining the cohomology of pair to be the cohomology of the co-cone construction. Now, co-cone can be defined explicitly as this chain complex, which is the sum of chain complexes with some shift in degree and some matrix, which gives you the differential. But the way to think about them is that they serve as some kind of a homotopy kernels. So they satisfy a universal property similar to the universal property of kernels, but only if you insert the word homotopy everywhere. So they serve as the replacement for kernels if you work in some category where everything is defined only up to homotopy. But still, in cohomology, we have an exact sequence, or exact triangle, if you want to say, from the relative cohomology to the cohomology of the first set, then restriction to the cohomology of the second set. What this shows us is if we are interested in kernels of restriction maps, those kernels come from images of maps from the cohomology of pairs. Now, what is missing to show the quasi-multiplicativity is the following construction. We have a product on the symplectic homology, and we want to lift it to cohomology of pairs. So we have to construct for A and B commuting a product from the cohomology of M relative to A, cohomology of the pair M and B, to the cohomology of M, of the pair M and the union. So this is the kind of similar to what happens with cup product in a classical cohomology. But in, say, in singular cohomology, since everything commutes on the nose already in chain level, you are not forced to work with these homotopies. And basically, one big part of the complication here is that you have to carry along all the homotopies and work with them. Now, why would you expect at all this commuting property to appear in the product? Well, the Meyer viatories that Varolgunes proved requires this pair to be commuting. Now, if you compare it with the Meyer viatories in algebraic topology, and for simplicity, let's consider Meyer viatories in homology, then we have Meyer viatories if and only if the pair is what's called an excisive pair, which means that the chain map from singular chains in A, from the sum of singular chains in A and in B to the singular chains in the union is an isomorphism in homology. So it's a certain condition that relates the chains on the union to some push out or pullback of chains defined on the summons of the union. And so the way to think about it is that commuting is basically the symplectic analog of this excisive pair condition, because it gives you algebraically the exact same thing. And similarly, classically, to have relative cup product, you need an excisive pair. So you have this product from a singular cohomology of M relative to A and M relative to B to M relative to the union. You need this excisive pair condition. So it's very natural to expect that we will see the commutation condition appearing in the construction of our extension of the product to pairs. So at that point, I conclude my talk. So thank you very much. And are there any questions?
Thank you very much, Yaniv. Are there any questions? So I wanted to ask about you had the example for commuting and non-commuting sets, and then you said that in dimension 2, if the boundaries intersect, then they're not commuting.
Yeah.
Do you have an example where it doesn't hold in higher dimension?
Well, I don't have one on the nose. I mean, I don't have something that I can construct like right now, but the thing is that in the paper by Varolgunes, he basically construct. Oh, of course I have. Sorry, just take the moment map and take let me draw. So if you take, let's see, how do I draw? Yeah. So if you are taking basically any involutive map, yeah.
Mm-hmm.
Oh, sorry, maybe I did not understand. You want two commuting sets whose boundaries intersect?
Yeah.
Yeah. So say take any involutive map, say I don't know, a moment map or something like that, and take just pre-images of two intersect sets in the moment map. So you will have maps. You will have sets whose boundaries intersect in M. And they are commuting basically because the pre-images of any sets under this. And more generally, in his thesis or in his paper also, Varolgunes gives you some kind of geometric construction telling you when to sets commute. If you can construct some kind of family of coisotropic manifold transverse to their intersection of boundaries satisfying something. So there is also some geometric manifestation of that. So you can think of it geometrically as that the boundaries are allowed to intersect as long as they intersect in some nice way. And this nice way is basically impossible to do in a dimension.
Okay, but what if we restrict ourselves to symplectic balls? So do you expect whose boundaries intersect and they're not the same ball, sort of?
So
do you expect them to
I don't expect them, because I think you will be able to just construct a commuting cover, and you can't have a commuting cover due to, say, non-displaceable fiber.
Okay. But can we show this, or?
So what, directly?
Yeah.
That they not commute? I mean, you want me
from
to...
the geometric thing that you said, Varolgunes. So you said like that Varolgunes has a...
No, so
geometric characterization?
His condition is more along the lines of if there exists some this and this construction, then we have commutation. But,
okay. I understand.
So I don't think I can at the moment just take two balls, let them intersect arbitrarily and compute their commutation. But well, maybe one thing that is important to note is the way that Varolgunes uses this property of commutativity is the following: that if he has two sorry, let me make it bigger. So if you have two sets in M, and say you have some kind of a radial increasing Hamiltonian here, and you have some Hamiltonian here approximating those sets. So you expect to have orbits kind of near the boundary going in each set. So the implication of this commutativity is that if you go to the maximum or the minimum, so say this was F and this was G. So if you go to max FG or to min FG, and now you get some kind of a bumpy thing for the union, you don't want to have orbits transversing the whole thing. So in 2 dimensions, this is hopeless, but in higher dimensions, this is possible. So this is the way it's being used, like if you open up all the boxes. So maybe this condition can give you some kind of intuition what to expect from the boundaries and their foliations, such that they intersect nicely.
Okay, thanks. And I have another question. So you said you have this quasi-commutativity, meaning only for the commuting sets.
Quasi-multiplicativity, yes.
Multiplicativity, sorry. So do you have any way to like measure how non-commuting things are by how distant they are from being multiplicative or something like this? Does it make any sense to look at something like this?
So, well, there has been already in Varolgunes' thesis. He constructs some algebraic gadget which vanishes if two sets commute. And this gadget basically measures how far we are from the Meyer-Vietoris thing. So one might try to, I don't know, maybe use torsion exponents or something like that to construct, at least algebraically, some measure of non-commutativity. But at this point, it is not very clear to me what it corresponds geometrically. So I don't have any, on the top of my mind, I don't have any geometric condition they can give you on the stats using Poisson brackets, using anything that will guarantee, for example, that this gadget will have a small torsion, so which is small torsion exponent is very close.
If the
zero because it corresponds to small bars in the homology.
So you can say something like if the Liouville vector field on the boundary is almost collinear and at the intersection point, then this should be small or something like this. You know what I'm saying? Like,
well, that would depend on how do you measure this almostness, you know, because it has to be some. Anything metric is not inherent to this. And also, I don't think this property would be local in terms of the intersection points, because say I have a sphere and let's take the equator and let me take two neighborhoods of this equator. Sorry. So I'm just drawing, let me just draw the front face. Okay, it would be easier. Back face is the same. So I have the equator, and say I have a neighborhood doing this and another neighborhood going like this. So each of those green things is non-displaceable. Sorry, it's displaceable. And the equator is of course non-displaceable. And from the Meyer-Vietoris sequence, if you compare it, you will see that at some point you will have to say something about those areas here. Yeah, but those areas here are not governed locally by the geometry of intersection. See, because I can have exactly the same angles and structure of intersection, distances, whatever notion you want, but having those sets intersect instead of a small neck by large disk. So I don't think that non-commutativity would be possible to be measured locally, but maybe
if you intersect on along a large disk, maybe you have more freedom to make sort of omega of the Liouville vector field smaller, or.
Oh, I see what you're saying.
I mean, I don't know. I have no idea.
It's something that I have to think about, so I don't have an answer on top of my head. But it's definitely a direction we want to check.
Can I ask a question? I kind of actually
Sure.
Variant of Shira's question. So
yeah,
I gather from your answer that the answer to my question is going to be kind of no as well. So there is this notion of a Poisson bracket invariant of a cover, which measures how non-commutative partition of unity is, which is for the covering is.
Yeah.
So that gives you a real number. Can you somehow make this an ideal valued Poisson bracket invariant of a covering? Can you produce something like that? Does it make sense to try to do something like that?
So there is again this obstruction constructed by Varolgunes. So actually he uses a very similar notation to our homology of pairs, which is unfortunate because this is totally different object. So I don't really know how to denote it. Let me just denote it for a second by SH of some collection of sets. So basically you can algebraically, it's an algebraic construction. You can ask, for example, what is the torsion, the largest torsion exponent here. And it's an interesting direction to check whether it's indeed related to the Poisson bracket invariant of covers or not. So this is something we definitely want to check, but at the point I cannot say anything informative about. And I think the main obstacle is that it's still not. It's very clear what is the algebraic implication of commutativity. As I said, it just has to do with certain solutions not existing when you go to the minimum or maximum. But even if you allow slight commutativity, it's not very clear at the point the relation between any metric measurement on the Poisson bracket and some algebraic consequence. So at a point, I can't tell you what I think or if there is any relation between those lemmas. I actually hope that there is, because it would be an interesting direction to approach a Polterovich conjecture if we had those tools at our disposal.
Yeah, or you
it requires further study.
Or you would have like an ideal value Polterovich conjecture.
In a way, yeah, actually, it would be a bit more complicated because we are talking about torsion here, and the ideal valued story considered kernels, which were lying in the symplectic homology. It was the quantum cohomology and didn't have torsion. But so one has to study a bit deeper this algebra to see what's going on, I think.
Okay, thanks.
May I make a little remark, right? So first of all, for covers, we have certain remark in the paper, right? So if the product of complements to the sets of the cover, of quasi-measures of the complements of the sets from the cover does not vanish, so then you cannot have commutativity. And and this is pretty easy kind of. So that's what one can check. How to get from this numerical invariance, I have no clue. And Varolgunes has very interesting, actually, so I would say much more sophisticated invariant for the collection of subsets. But the problem with this invariant is that it's completely unclear how to calculate it in very simple examples. So because you have to basically do some first to make some cubes and then make some cones, and so then algebraic object becomes already pretty complicated, I would say, for three-dimensional cube. So calculation becomes elusive, and I think we discussed a little bit with Umut this, and it's yeah, it's a very interesting idea how to advance in this direction.
Okay, thank you.
Welcome.
Yaniv, thank you very much